Howdy. So I'm super excited to introduce our last speaker of the semester, Ryan Sun, from the University of Texas, MD Anderson Cancer Center. So he's currently an assistant professor of biostatistics and data. He's also an adjunct faculty member at the Department of Statistics of Rice University. Ryan got his bachelor's degree in applied maths from Columbia University in 2012, and then he obtained his PhD degree in biostatistics from Harvard University in 2017, and then he completed a postdoctoral training there, and then he joined MD Anderson in 2019. So Ryan is a statistician working at the frontiers of biomedical data analysis. So he develops novel statistical methodology for analyzing all kinds of biomedical data sets. And currently he's working heavily on those really huge biomedical data sets, for example, the UK Biobank. As a junior researcher, Ryan has a very amazing publication list. So he has done methodological works published in JASA, and he has a bunch of papers in Nature journals and publications in every top journal in statistical genetics. He has also developed a couple of R packages which are super useful to the biostatistics and probably the biology communities in general. So today he's going to talk about the large-scale inference for composite null hypothesis in genetic association studies.
Yeah, thank you so much for the very kind introduction, and yeah, thanks everyone for coming today. I'm going to be talking about genetic association studies and testing for composite null hypotheses. It's work done with my statistical collaborators, Zach McCaw and Shihong Lin. And then we're able to work with a really great translational lung cancer group at Baylor College of Medicine, the Chris Amos group, and csmGmm is also part of that group. So feel free to interrupt me at any point if you have a question or I say something too fast or I use some jargon that doesn't make sense. So I thought I'd start by just introducing the types of data and problems that really motivate the work I'm going to be talking about today. All of it comes from Germline genetic studies, or people say statistical genetic studies. And I'll just describe it, at a high level very briefly and then get into more specifics. But sort of the core goal of statistical genetics is just to understand how differences in our own personal DNA, our own personal genetic code, contribute to differences in observed traits. So for example, your hair color, your personality, your risk of cancer or other diseases. So you've probably heard like the common facts that we each have about 3 billion different locations or 3 billion different pieces of our DNA. Between any two people, about 99.9% of them are going to be the same. But still, that means there's millions of differences between any two people. So for those differences, we call them mutations, variants, SNPs, single nucleotide polymorphisms. They're all synonyms for the same thing, just genetic mutations. And then when you have a larger sample, like 1,000 or 100,000 people, there's going to be tens of millions of mutations that are different in that sample. So it's clearly like a high-dimensional problem. You have these tens of millions of genetic features. You're trying to figure out how they affect different traits. And statisticians like it. And it's a hard problem because genetic effects are famously very tiny. You have, the effect of any given single mutation on any single trait is going to be very small. So for a long time, or if you maybe haven't heard a statistical genetics talk in a while, for a long time, a lot of the research was focused on these designs for testing global null hypotheses. So by global null hypothesis, I mean you have these multiple parameters, alpha, beta, gamma. The individual null is that alpha equals 0, beta equals 0, gamma equals 0. The global null is that they're all 0. The alternative is just that at least one is non-zero. And so people do this for a couple of reasons. One, the effect sizes are very small, so it's nice to bring together more data sets, have more power. And then two, the cost of collecting genetic information was very expensive. So it'd be a big study if you had like a couple thousand lung cancer patients. So what people might do is like you're testing association between a genetic variant, a single genetic variant and lung cancer in like an MD Anderson cohort, and that's alpha. And then you might have like a cohort at Michigan, and that's like beta. You might have a cohort in Europe, that's like gamma. And you're just bringing all that data together to increase your power to detect these associations. And so for a long time, there was a lot of statistical work doing this global null testing. You might have heard of like the higher criticism, the aggregated Cauchy association test, a lot of this work in rare weak signal detection. So more recently, we found that our collaborators actually are very interested in study designs that want to test composite null hypotheses. And this has been a shift just very recently. Again, for another couple of reasons. The technology, the cost for acquiring genetic data has fallen by over an order of magnitude. And then also governments and like international organizations are spending a lot of money to pursue like personalized healthcare, personalized medicine. You've heard the buzzwords. And so, for example, like in the UK, they have things called like the UK Biobank. It's publicly available. They have 500,000 people. You can get all their genetic data, tens of thousands of biomedical outcomes. So the sample sizes are all of a sudden, 1 to 2 orders of magnitude what they were even just like 5 years ago. So now anybody, you can just jump through some hoops, download the publicly available data. You can just do like logistic regression. You don't need anything special. You can find hundreds of variants that are associated with lung cancer at like very small p-values, like 10 to the minus 10 or even stronger. So what we've really seen is that our collaborators are really interested in testing these composite null hypotheses now, where the idea is that the null hypothesis now is that at least one is 0, and the composite alternative is that they're all non-zero. So I'll explain with some more specifics now. So the first one, I'm going to be borrowing a little bit from causal inference language and diagrams. The first very popular study design that people care about now are these genetic mediation studies. And the idea is that people want to find what they call this natural indirect effect. They want to find this pathway, basically, where a genetic variant affects gene expression. So gene expression is just like the amount of a gene you make. And they think the gene expression affects like lung cancer. So the genetic variants in your body, they control what types of genes you have. So like what color of hair you have, and also like how much you make. So like when you get sick, you get COVID, the amount of immune response you have, the amount of like immune antibodies that you produce is what they call gene expression. And so how much of that depends on your personal genetic code. And crucially, it can be modified by like medicines and things. So you can't really change your baseline genetic code because that's just what your mom and dad gave you. You can't intervene on that, but you can intervene on gene expressions. There's medications and all sorts of things that can upregulate or downregulate it. So people care a lot about defining this pathway, what they call the natural indirect effect, because if you define that this pathway exists, then if you block it at the gene expression level, then you can maybe reduce mortality or morbidity of lung cancer. So this is a composite null hypothesis testing problem because you need to know that both of those arrows exist. Both the alpha and the beta exist for you to have this natural indirect effect. If one of them exists, then you don't have this mediation problem. You really need both of them to exist. And so what people do is, they feel like very simple just regression models, right? So the expression is a continuous number. So just fit like a linear regression model for the gene expression, and then you might fit like a logistic regression model for the second arrow beta. You have these two regression coefficients like alpha, beta, and you try to come up with some way to test that they're both not equal to 0. So often that's just like you take like the product alpha times beta as like a test statistic. Is that not equal to 0? And so this has been the focus of a lot of literature recently in the statistical journals. A second very important type of composite null design that people are interested in is pleiotropy analysis. So what genetic pleiotropy means is that you have a single variant that's associated with 2 different diseases. So it's gained a lot of popularity recently because you may have heard that there's some they call them miracle weight loss drugs now that were originally developed for diabetes. But people are taking these drugs now and they're just losing a lot of weight, and it's good for really obese people. Similarly, in lung cancer, they originally developed some drugs for like heart disease, but they also found that when they did these trials that it was actually very good at preventing lung cancer. They published them in like the New England Journal of Medicine. So if you can figure out that some of these genetic variants, that some of these biological processes are affecting both diseases, then instead of spending billions of dollars to develop it, because it costs billions of dollars and years of time to get a drug through all the FDA approval and stuff, if you can figure out that these underlying biological processes are the same, then you can save a lot of money, save a lot of time, and just repurpose the drug. And so here we have a composite null framework also, because you don't care if the variant is associated with just heart disease or just lung cancer. You only want to find the variants that are associated with both. So again, you're testing the composite null, the composite alternative. People are very interested in this in lung cancer. They already calculate like genetic correlations, which is basically like genetic similarities between like lung cancer and a lot of different outcomes, in hopes that they will be able to find these types of variants. But the actual inference for the specific variants is very hard to do, and I'll show you why. A third type of study design that people care a lot about is just replication analysis. So when you do omics research, a lot of times people will say like, oh, I discovered this risk factor for cancer, I discovered that risk factor for cancer, but you always have to replicate it because there's a lot of type 1 error in these studies. So our collaborators, for example, they might go into the UK Biobank, they might say like, I found this association with lung cancer, I did like a wall test, just like linear regression, I got a Z statistic of like 4.5, and then I want to replicate it, so I go to this other biobank, like the Million Veterans Program, they have publicly available data on 1 million people. They said I replicated it, this Z statistic 5.4, but then they go to their own internal data, Baylor College of Medicine data set, and they say, but this test statistic, it's in the opposite direction, it's negative 4.1. So they say, if I looked at these two data sets, I kind of have replicated it, but if I look at this third one, then like my direction is in the opposite way, like do I have replication? And so can I do some sort of formal hypothesis testing that's better than just looking for like test statistics that are large in each data set? And I want some way to do this. So the mediation problem is like the simplest form, because there you just have alpha and beta, you always just have the two arrows, and you can show that those test statistics are independent. The pleiotropy and replication problems are a little bit harder because you might be interested in 3 outcomes, 5 outcomes. So the dimension of your composite null set is larger. Your test statistics might be correlated if you're using the same data set. So it can get more complicated than just the mediation problem, but a lot of the literature is in the mediation problem because it's the most straightforward and easy to understand for now. So why is it hard to do composite null testing? Why can't you just do like a wall test or a likelihood ratio test to do this type of work? I'll try to explain it here briefly. If you think about you're in like the mediation setting and you just fit your 2 regression models, you get your favorite estimator of these parameters alpha hat and beta hat. Generally, you appeal to the central limit theorem, you find that they're normally distributed with some unknown mean invariance. And so maybe you take T, you take your test statistic as the product of them, and you try to test that it's not equal to 0. You can write down the characteristic function of T, and you can see that it depends on that mu alpha and mu beta. So it depends on like those true unknown means. So the problem is that in the composite null setting, you don't have this single reference distribution that you can use. So in the global null setting, people say the global null is just all of them are equal to 0. So your null space is just that point at the origin. You can get your reference distribution is just like chi-squared 1 or chi-squared 2 or whatever it may be. When you're in the composite null setting, you have these 3 cases where you can be under the global null where they're both 0, and then you can be in case 1 where the alpha is 0 and the beta is not 0, or you can be in case 2 where alpha is not 0 and beta is 0. So your composite null space is infinitely large. So you can see that the composite null space is just both axes. And if you try to do like a standard frequentist test, like a log test, like a likelihood ratio test, you have to pick like a point in that null space and hope it approximates the entire null space well. And often that approximation, it doesn't work well. And people have shown it a lot of times. So you might have heard, if you do mediation analysis, something called like the Sobel test is very popular. In psychology, they use it a lot. In pleiotropy analysis, they use something like, they call it the maximum p-value test. These are, again, all like wall type tests for the composite null effect. And so what you can see here are like QQ plots. So where QQ plot is, so each dot there is like a single composite null test. Like each dot is the result of testing like one genetic variant against heart disease and lung cancer. And so you would expect those points to follow along like the x equals y line, which would mean that they're uniformly distributed. And so you would expect them to be uniformly distributed because we know that most genetic variants are not associated with both lung cancer and heart disease. Only a small number are. But you can see that because they fall below that line, it's telling you that these tests that you're doing, you're not producing p-values that are uniformly distributed. And this comes up over and over again whenever people try to do this type of composite null testing. And so it tells you that all of these traditional methods are not working very well. So in the literature recently, people have proposed trying to do these more specialized approaches. They have what's called the divide aggregate composite null test, the high dimensional mediation test framework. They're both actually very similar. The idea is just to estimate the proportions of each case 0, 1, 2. And then the idea is that if you can estimate the proportion of each case, you can use it in your test statistic to do a little better inference. And they do work better than what we had before, but there also are challenges, just the standard challenges of trying to do this frequentist inference in this composite null setting. So one alternative approach that we have found more appealing is to try to employ this empirical-based two-group idea. So the two-group model is a very famous model in omics studies. The idea is just that you have this unobserved binary variable h. H denotes like the status of the hypothesis. So H is 0 if there's no association. H is 1 if there is a true association. And then the distribution of your test statistic given no association is just normal 0, 1. The distribution given that there is an association is just some other distribution F1. So you can calculate the probability that H equals 0 given your observed data. And that's what they call like the local FDR, the LFDR. And it's very similar to the traditional like Benjamini-Hochberg false discovery rate, a little bit different, but it's interpreted the same way. The probability that the null is true given your observed data. So it's a very popular model in omics types of studies. It's very simple, straightforward to understand. There's two groups. H is just 0 or 1 if there's an association or not. So it's nice for our setting too, because it extends very well to these composite null settings. Because you can imagine instead of H being a single scalar random variable, if I'm in like the mediation testing setting, now my H, maybe I can just make it a two-dimensional vector, two binary random variables. The first one tells me about the alpha, the second one tells me about the beta, the two different effects. So now I can explicitly write out what my full hypothesis space is. I can write these 4 different cases down, and then the first 3 are in the composite null. The last one is my composite alternative. If I want to do more complicated settings, like the replication testing or the Pleiotropy setting, if I have 3 dimensions, 4 dimensions, it's very easy to write out all the combinations of 0s and 1s. And again, it's very interpretable in that sense. I can explicitly account for each of these different cases. And then to introduce directionality, instead of a 2-group model, I can do something like a 3-group model, -1, 0, 1, where -1 tells me the direction is negative and +1 tells me that it's positive. So it extends very well. It's very flexible to the types of genetic association settings that we care about. So the big problem when you try to do this in practice actually is that you have to do some multivariate density estimation. So density estimation, even in 1 dimension, is hard. And then in multiple dimensions, it's even harder. So a lot of times when you read these papers, they just say, just use a consistent density estimator, or just plug in a kernel density estimate, use a natural spline or something like that, and then everything works out nicely. But in practice, it doesn't. It's very hard to figure out what type of estimator should I use for all these different sets of problems. And in particular, like you get images like this. This is just like one representative estimate, where like the blue line is like a standard normal density. The green line is like when we try to estimate the density of our lung cancer test statistics, and the red line is for heart disease. And it's not clear if this is good or if this is bad, or if we can do better, or what type of estimate that we should use. And then in particular, the one thing that our collaborators cared about most was the interpretation, because they found that when we would give them these results, a lot of times the empirical Bayes multiple testing rule is contradicting the frequentist testing rule. So for example, if you're doing this analysis of association with lung cancer and heart disease, you might have 2 variants. One is associated 4.5 and 4. These are standard like walled Z statistics in your linear regression. And the variant B might be 4 and 4. So you would think like, obviously, okay, 4.5 and 4 should be rejected if 4 and 4 is rejected. That's just like our intuition about multiple testing in frequentist settings. The problem was that actually, depending on how you estimated your density, often like the 4 and 4 would be more significant in like the empirical Bayes multiple testing rule than the 4.5 and 4. And this is a very big problem, especially in genetics, because in genetics, everything runs through these Z statistics. They call them summary statistics. If you ever do genetics work, like the first thing that people do is download these millions of different summary statistics for millions of different diseases. So it's very puzzling to them when they try to publish their paper. You say, okay, this is my mediation result, or this is the Pleiotropy testing that I did for you. And they say, okay, how come you rejected 4.5 and 4, but you didn't reject 4 and 4? Like, the reviewers are going to care about this. And even as statisticians, we can understand, because as statisticians, we like it when frequentist and Bayesian methods agree also. So a big drive for the work that we're trying to do is to come up with some way of implementing this type of composite null testing framework in practice, where we can develop some sort of density models that's, you know, still flexible enough for all of these different settings, that's going to possess good operating characteristics for each of these different problems, and is also going to be interpretable, because that's the thing that our collaborators care about the most. So the way that we go about trying to harmonize the test statistics in the frequentist setting and in the empirical base setting, so a lot of density models or density estimation techniques, they're going to penalize like the degrees of freedom. They're going to make it a certain smoothness or make it a certain jaggedness. So what we were trying to do actually is find a penalty or find some constraint that gives us this interpretability, that gives us a more interpretable model instead. And so what we land on is what we called this conditionally symmetric multidimensional Gaussian mixture model. And so as the name suggests, it relies on this conditionally symmetric formulation, basically. So I'm just going to describe it in like the very simplest mediation setting. The idea is that we rely on this assumption of symmetry between association configurations in the same category. So if your association is in the same place, then the distribution of your test statistics is assumed to be the same. So like here, I have like H1 and H2, like 0, -1, and 0, 1. So that means like the alpha portion of that mediation testing is null, and then that beta portion, the second arrow, is either negative or positive. So the key assumption is that because those associations are in the same place, that those statistics are going to have the same distribution, just negations of each other. And then also I have like H3 and H4, -1, 0, and 1, 0. That means there's the association in the alpha parameter, and then in the beta parameter, there's no association. I'm going to say those test statistics come from the same distribution, just negations of each other. Then for the alternative, the 5, 6, 7, and 8, there's associations in both the first dimension and the second dimension. So I'm going to say again that those test statistics come from the same distribution, just negations of each other, depending on the exact configuration. So you can imagine if I have more dimensions, like 3 dimensions, 4 dimensions, I'm just adding like zeros and positive ones or negative ones, and the symmetry flows in the same way. And we say the symmetry flows through this binary representation, where if you just take the absolute values of the elements of H and you think of them as a number in binary notation, so like 0, 1 is 1, 1, 0 is 2, and then 1, 1 is 3, our symmetry is conditional on these binary representations. And that's really the key assumption that our model is built on. It's nice because in genetic association studies, the directionality is really arbitrary a lot of times. It just depends on the person's data cleaning pipeline. So it's sort of like, you know, if you do a study like male and women, which one are taller? You can say like male is coded as 1 or male is coded as 0. And then if you code it as 1 or 0, then, you know, the effect is going to be positive or negative. But it doesn't, the information is the same. It's still, it's just coded as positive or negative. So it's very similar in genetic association studies, where people will just code the direction of the effect as positive or negative, but, and they'll just do it differently depending on their own data cleaning pipeline. So the symmetry assumption, it actually makes sense in practice. And also, even if it doesn't make sense, you can also sort of just flip the data a little bit until it does look symmetric and you don't lose any information. So we consider the model. So basically, we consider each piece of the model separately, where each piece is like each case 0, 1, 2, 3, or 4, the binary representation. So maybe I'll show the picture first because it's a lot easier to understand. So like if you're in that case 1 setting where the alpha parameter is 0 and the beta parameter is like -1 or 1, we just assume in that first dimension you're just a standard normal 0, 1 distribution. That's your contribution to the mixture. And then if you're in that second dimension where the beta is -1 or 1, we assume that it's just a mixture of these symmetric Gaussian distributions. So Gaussian mixture model, like very famously, can very flexible, can accommodate many different distributions. So that's sort of the motivation for doing this mixture type idea. But you can see, so we allow the user to specify the number of mixture components, but we constrain that the mean magnitudes on the positive and negative side are the same, and we constrain that the mixing proportions are also the same. So that gives you the symmetry idea. So you can see, like in the first line of the equation, it's like the 0, -1. So then that's where you have those negative means in the second dimension, and then in the second line you have like 0, 1. So then you get those like positive means in the beta part, and in the alpha part you just have the zeros. So it's just standard normal 0, 1 always. So then if you consider like case 2 where alpha is not 0 and beta is equal to 0, it's the same idea, just flipped. So like when beta is 0, that just means the contribution to the mixture is just this standard normal 0, 1. And then in the alpha portion where it's non-zero, in that first dimension, you have this mixture of Gaussians. It can be more than 3 mixtures, but I just showing 3 on the page right there. The user sets that number, but basically it's the symmetric mixture again, where the mean magnitudes are the same, and then the mixing proportions are also the same for the negative and positive parts. And so that creates, you can see that conditional on this like binary association status representation, we put this symmetry constraint on. So like the global null piece where both alpha and beta are 0, we just make it so that it's a standard like bivariate normal distribution with 0 means. And then the alternative portion where both dimensions have an effect, this is the composite alternative. It's basically going to be the same thing again. In both dimensions now you have this mixture of symmetric Gaussians where the negative and the positive means are the same, and then the mixing proportions are the same. So that's the basic structure of the model. And I wrote it down. You can actually write it very compactly for any number of dimensions. You can just sort of imagine in your head, like if you add a 0, then you add that normal 0, 1 component to the mixture. And if you add like a 1 or -1, you just add those mixture of Gaussians. And then we make the final assumption that under the alternative, your means are not smaller than under the null, which is reasonable because if you have a variant that affects a lot of different things, it's probably going to have a larger effect size. So to talk about what we get, the benefits of this type of model, we make one definition first. We define what we call an incongruous result. And that's basically like the example that I gave earlier of you have 2 variants, one's 4.4, one's 4.5. We say you have an incongruous result if you do this empirical Bayes analysis and the local false discovery rate is smaller for the Z statistics, the frequentist test statistics that are less extreme. And so it's basically just saying that your multiple testing rule doesn't agree at some point when you apply the 2-group model. So that allows us to prove a few different things. So basically the first theorem says that if you apply this model when you're doing the composite null inference, it prevents the contradictions between the empirical Bayes and frequentist significance rankings when you're doing mediation analysis or Pleiotropy analysis when the test statistics are independent. So you get that guarantee of interpretability. It's never going to happen anymore that like the frequentist Z statistics and the empirical Bayes local false discovery rate disagree. So that's the big benefit that you get from this model. And then we make a couple of extensions because sometimes the test statistics within a set are going to be correlated. So for example, like if you just test 2 correlated outcomes in the same data set, like Z1 and Z2 are going to be correlated. So in that setting, the correlation introduces a lot of complications. And so we only define a model for the 2-dimensional setting. Basically, if you have this positive correlation rho and you have a 2-dimensional correlated bivariate normal, we can prove that using this type of model on correlated data to do the multiple testing prevents the incongruous results in the tail. So that's nice because the tail is the area that we care about anyway. If you have test statistics that are near 0, they might still disagree between the frequentist and empirical Bayes approaches, but those are not going to be significant, so you're probably not going to be reporting them anyway. You're only going to be reporting the stuff in the tail. And so the area of the tail depends on like the correlation structure and some other parameters. So finally, we talk about the replication setting. So in replication analysis, the composite null is even larger than the general composite null. The composite alternative is smaller because the direction really, the direction matters. The composite alternative only has two pieces. It only has the piece that's 1 everywhere, and it has the piece that's -1 everywhere. So there's always only two pieces. So basically, you have to put some more restrictions on the model so that you get these nice properties. But basically, it's the original conditionally symmetric multi-dimensional Gaussian mixture model. And then we just add the additional restriction that the number of alternative mixture pieces must be 1. So instead of like the 3 mixture pieces or the 2 mixture pieces that I showed on the alternative, you have to constrain yourself to 1 mixture piece in the replication setting. And then, oh, that should say, oh, I went the wrong way. Okay, yeah, so theorem 3. And so then the third result we can come up with is that if you're doing replication analysis with the replication composite null and the replication composite alternative, if you use this model, the replication csmGmm, we guarantee congruous results when all observed test statistics possess the same sign. So again, that's the important part, because if you do replication analysis and they're in different directions, it's not going to be significant anyway. That's not what you're going to be reporting. You're only going to be reporting the significance results when everything's already in the same direction. So this is, again, like the tail part that we care about. Oh, wrong way. Yeah. So to actually like fit the model and do parameter estimation and all of that is also a very difficult problem that I actually won't talk about too much because there's a lot of work out there that's focused specifically on like fitting these models and convergence rates and so on. But basically, in genetic association settings, you also have correlation between the genetic variants. So from once there's correlation within sets and there's correlation between sets. And the correlation between sets is very hard to deal with, very hard to model, very hard to write down in some kind of closed form. So we just appeal to some like composite likelihood arguments, and we just ignore the correlation, basically. So we just write everything down as if the correlation between the SNPs, between the genetic variants is non-existent, and actually it seems to work okay. But you can just write down the likelihood, and then the unknown mean parameters and the unknown mixing proportions, we just iterate through like an EM algorithm to get to the final values. And then we just take like one more iteration of the EM algorithm to calculate these local false discovery rates to do the analysis. Yeah, so in simulation, we compare against some of these recently proposed ideas. So like the high dimensional mediation test, which is estimating the proportion of every null case. We're comparing against the divide and aggregate composite test, which does a very similar thing. We also look at doing this 2-group model, but with just like a standard kernel density estimator, which a lot of people recommend. We also consider estimating the density using natural spline with 7 degrees of freedom and 50 degrees of freedom. And so this comes from like the local FDR package on CRAN. So the overall sort of take-home message from the simulations is that if you use some of these other density, the common recommended off-the-shelf density estimators, sometimes they work well, and then sometimes they just completely blow up on you. So like in the mediation setting, so those top 2 rows are, I'm showing there's no composite alternative, and you can see that like everything's just very conservative if you're using like a nominal false discovery rate of 10%. And then the bottom 2 rows, I'm adding some alternative sets. And you can see that like some things just blow up on you, like using 7 degrees of freedom natural spline. Sometimes you can't protect the nominal error rate when you use this like divide and aggregate composite null test. Again, sometimes it just blows up on you and you can't control the nominal error rate. Similarly, when you think about larger sets of larger sizes, like here I'm showing 3 dimensions in the top 2 rows. So you can see that using like the splines or the kernel density estimation, you just can't control your nominal false discovery rate, and even at very small effect sizes. Whereas with like the proposed model, actually we're able to control it pretty well. And then when you talk about the setting of like correlation with insets, you talk about the replication setting. Sometimes, yeah, it's hard to predict like which one is not going to work well. But in general, across the different settings, something is not going to work well. Except we do find that we have this pretty nice robustness with the solid red line, which is the proposed idea. Again, Gaussian mixture model, well known for being flexible enough to approximate a lot of different distributions, and we'll just put that key symmetry constraint on it. And then if you think about, the story is mostly about protecting the nominal false discovery rate. If you look at power, actually everything pretty much performs well in terms of power. All the methods are basically able to find like similar amounts of composite alternative sets. So we don't really find that there's a difference in power. Everything performs the same. And then if you look at the bottom row, I'm plotting like the number of incongruous findings across these different experiments. And there's like 100,000 tests performed each time. And so you can see that like there can be 1,000 or 2,000. So like 1 or 2% of the results can be incongruous. Like there's contradictions between the empirical Bayes analysis and the frequentist multiple testing analysis. So there can be a lot of confusion across these settings, except if you use the proposed model, which the constraints make sure that the contradictions don't happen. Yeah, so we applied it to 3 different applications that our collaborators were very interested in lung cancer. So the first one I described already, just this mediation analysis, trying to figure out which pairs of genetic variants and gene expressions are contributing to lung cancer risk. We had data from the International Lung Cancer Consortium for that. We did a pleiotropy analysis between lung cancer, heart disease, and BMI. So people are very interested in these 3 diseases because they think that there's overlapping medications that can be used for each of these diseases. They show a lot of genetic correlation. So people think that they're very similar genetically, and we use the UK Biobank, and we use a cardiogram consortium data set. And then we also try to replicate our lung cancer and cardiovascular disease results. So you can see here, this is like when we do mediation testing, these are the 5 significant pairs that we found. So like the original motivator for this analysis was when we looked at the 2nd and 3rd lines, and we were just trying to use like the spline density estimates. And if you just use like a spline density estimate, you can see like the 2nd line is clearly more extreme than the 3rd line. 2.85 is greater than 2.65, and negative 4.4 is less than negative 4.18. But if you use like an off-the-shelf estimator, it's going to reject the 3rd line, but not reject the 2nd line. And so that's the original sort of finding that our collaborators came to us with and said, we could never try to publish this. It doesn't make sense. But these are the 5 findings that you find when you do mediation analysis. We then performed some pleiotropy analyses across the 3 diseases, lung cancer, heart disease, and BMI. So actually you can see that if you do the 3-way analysis and you use the proposed idea, it doesn't find anything significant at all. And the other ideas are going to find like a couple hundred significant genetic variants. And this is out of like about 8 million tested variants across the genome. Of course, there's no way to know. It's just one real data set application, but we would think that based on the results of the simulation, some of these other methods are just not able to protect the error rates, especially when you have more dimensions. Like 3 dimensions is just much harder than estimating a 2-dimensional density. And then of course, you go more dimensions, 4 or 5 dimensions, it becomes much, much harder to estimate these densities. And we saw the off-the-shelf methods were doing worse and worse as you introduced more dimensions to the problem. So we also did all the 3 two-way associations between lung cancer and heart disease. And then we did lung cancer and BMI, and then heart disease and BMI. You can see actually all the other methods are still finding hundreds more associations in the 2-way analysis. We did some adjustments to try to estimate how much additional error, or how some of these other methods were unable to protect the nominal false discovery rate. And so we did some adjustments based on these simulations. And after the adjustments, you can see that the numbers actually look pretty similar, which is in line with the simulations that suggest everything has approximately the same power when you do control the error rate. So yeah, these are the visualizations of our findings. So this is like a very common plot in genetic association studies. It's called a Manhattan plot. So each dot is one genetic variant, and it just visualizes where the risk factors are along the genome. So the y-axis is like the negative log of the local false discovery rate. So higher is more significant. So you can see that there's these risk factors, joint risk factors for lung cancer and heart disease on chromosome 15. You can see that there's these joint risk factors for lung cancer and BMI on chromosome 6. So that's like well-known. Chromosome 6 is where like your they call it the major histocompatibility complex. It's where like whenever you hear about people need to like match their immune markers, that's chromosome 6. That's what we're talking about. And then you can see like there's scattered pockets of two-way association across the rest of the genome. The figure on the right is plotting just lung cancer and associations with heart disease. So the orange squares are everything that's replicated in two different independent lung cancer data sets. So you can see there's a lot of lung cancer specific risk, but then the blue points are associations that are both lung cancer and heart disease. So you can see like the proportion of joint risk factors for both diseases is very small compared to the number of orange points, which, you know, it makes sense that only some small proportion of these lung cancer risk factors are also risk factors for heart disease. So yeah, so you can see that the plots look fairly similar as you would expect. And so this is the type of plot that we give along with the tables to our collaborators and to show them, you know, where we think these risk factors are. And then I don't show the QQ plots, but if you look at the QQ plots, actually everything looks very nice compared to the ones that I showed before. So yeah, our software is online. It's on GitHub. You can download it and take a look and try it if you want. It's very fast, I'll say, or relatively fast for the sample sizes we're doing. You can do like 10 million tests on your own personal computer. And then more than that, we haven't had data that looks like that. But yeah, yeah, thanks for your time. Thanks. Appreciate it.
Yes.
It's more of a clarification question. So you are saying that your approach does not contradict the frequentist approach.
Yeah.
So when you are talking about the frequentist approach, like what is this actually doing in this case?
So yeah, just like, I guess it's not a formal frequentist multiple testing correction, but you know, in general, in the frequentist testing, if you have a test statistic that's more extreme and in the same direction as another test statistic, if you reject the less extreme one, you would also reject the more extreme one, because that's how you define a rejection region. It's a certain point, and everything that's more extreme than that point, you reject. And that's like the standard frequentist way of doing multiple testing. But when you compare it to like the local false discovery rate, you'll find pieces in your grid where something will be more extreme and it won't be rejected, but something will be less extreme and it will be rejected by like the empirical Bayes approach. And so that's like a contradiction in the sense that, yeah, the two approaches are not agreeing on the rejection region.
Okay, so in this situation, when you are talking about, say, multiple hypothesis testing or FDR, but in the formulation, you just have your alternative is not composite, right? So it is just one thing. So when you are doing this multiple hypothesis testing in the frequentist approach, so I am kind of trying to understand like what does that mean? So because you can just have only one alternative.
Yeah, so when people use like the divide and aggregate composite test or the Sobel test in the mediation setting, you have two test statistics from your regression models, like 3 and 5. And then those tests combine the 3 and 5 into like a single measure of significance, basically. And those measures of significance, like generally, like if you compare 3 and 5 or 3.1 and 5, the 3.1 and 5 is going to be more significant. And that's the standard intuition about working with summary statistics, is that if you have a set of summary statistics and they're both in the same direction, the same sign, and one is more extreme, then if you reject the less extreme one, you should reject the more extreme one.
Coming from the formulation of those frequently summary statistics.
Right. And people use summary, they're like ubiquitous in genetics research. Yeah, everybody uses them, makes them available for download. Yeah.
Thank you.
Thanks. Yeah.
Yeah, thank you for the talk. It was very nice. Did you do any power analysis comparing it to like whether it's making like high number of true detections in comparison to the other existing methods?
Yeah, so I kind of went through it really fast, but yeah, the power plots, if you look at them, it's just like the top 2 plots here. Like the lines are indistinguishable, you can't tell them apart. So basically, the advantages are in that you get the nice false discovery rate control, and you don't have to deal with these contradictions. Yeah.
I have a second question.
Yeah.
So I know DAC tends to get a bad reputation because there's a couple of mistakes in the GitHub code.
Yeah.
Like,
yeah.
like I'm just like trying to like understand like the cases where DAC does not control the FDR.
Yeah.
Like I'm just trying to, never mind.
Yeah, it's there are some errors in the GitHub code, but the author will provide you with the updated package if you email him. Yeah. I did email the author for the updated code.
Any more questions? If not, let's thank Ryan again for his